My name is Richard Heyns. I'm the founder and CEO of Brytlyt. And what I'm going to be talking about today is our GPU accelerated database and our visualization workbench that uses GPU acceleration for analytics. So just a show of hands, who is familiar with GPUs? Cool, good. Okay, good stuff. Right, so GPUs have been used for a number of years for non-graphic workloads. And what Brytlyt does is use GPUs for SQL workloads, so relational databases. The GPU accelerated database is the next evolution in high-performance databases. Right in the beginning, you had punch cards, and the most recent are in-memory solutions. And the GPU accelerated solution is taking that to the next level. Two reasons why. One is the fantastic compute that GPUs have available. So that's at graphic peak flops. The orange line is GPUs compared to the high-end CPU system at the time. The blue line in that is Moore's law. So GPUs are outstripping Moore's law in acceleration, which is pretty impressive. The other graphic there is memory bandwidth. And that's really important for databases because it's actually how quickly you can get data onto the cores and processed that really matters. And we are seeing performance improvements of around about 300x on a standard disk-based solution that you might get from Oracle or Microsoft. 300 times is pretty significant. It means that a query that might run in 5 hours can now run in under a minute. Why is that important? Well, this guy over here finds it really, really useful. Almost 2/3 of a data scientist's time or an analyst's time is spent actually working with and preparing data. Only 3 days a month is spent on the interesting stuff, which is mining and refining algorithms. Almost 40% of an analyst's time, it takes more than a week to generate a piece of insight. So somebody comes in on a Monday morning with a bright idea, and by the end of the week, Friday afternoon, they go home and they still haven't yet resolved that idea or dug down to the bottom of it. And interestingly, SQL is still the most common technology used in data science and data processing. That was from a survey, a recent survey. There are two other key points that came out of the survey, key pain points. The first is the biggest pain point is flexibility and how useful the tools are to data scientists. And the second pain point, second most important one, was performance. So 1 in 3 analysts were saying that they had to deal with slow running queries. And it's very likely that these two pain points is the reason why it's taking so long to turn data into insight, time to value, right? So what we're talking about, well, basically analyzing billions of rows of data in milliseconds. And that's really important for two groups of users. One are business leaders and decision makers who are using dashboards to give them up-to-date information in contextual awareness and situational awareness, and also analysts and data scientists who day in, day out are working with data and finding that that is just taking up a huge amount of their time. So this requires a radical new think in the status quo. And just to get a perspective on how fast, ultra fast is, if you think of Usain Bolt, world's fastest man, in the starter's blocks, and the starter's gun goes off, it takes Usain Bolt about 155 milliseconds just to start moving. And if he moved any sooner, he would be disqualified because human perception is in the realm of 120 milliseconds. And in that time, in 5 milliseconds, in fact, for some of the workloads, we've been able to process 1.1 billion rows of data. The great thing about GPUs is that they parallelized thousands and thousands of cores. And that's where they get their fantastic compute characteristics from. But it also is a real technology challenge that needs to be overcome there. And Brytlyt is the only vendor in this space to have patent pending intellectual property to address these kinds of parallelizable challenges. We've done some benchmarking against other vendors in this space. This is an independent benchmark run by a third party, same queries, same data sets. Those times are in milliseconds, 1.1 billion rows of data. Okay, fairly straightforward types of queries, but we were using indexes on the GPUs to really accelerate performance, and this shows that we are between 4 and 5 times faster than other GPU vendors. And bearing in mind that the GPU space is already exceptionally fast, this is a fantastic accomplishment. But it's not just indexing that allows us to run really fast. These queries were run without indexing and still significantly faster than other vendors in this space. Just a little bit about indexing. Because it's all in memory and in GPU RAM, our indexing is based on pointers. And so whether you create an index on one column or if you create a covering index on a number of columns, the size of the index is actually the same and also relatively small, which is different to what you'd normally see in a disk-based solution. In a disk-based solution, you actually make an entire new copy of the data and rearrange it in a way that makes sense for accessing it. One of the strengths within our IP, the patent-pending IP that I talked about earlier, is our ability to do joins, fast joins on GPU. So joins is one of the things that is really difficult to do in parallel. Sorting is quite easy, aggregating is quite easy, grouping is the form of sort. But joins, when you're bringing different tables together, is actually really difficult to do in parallel and quickly. And so this is, the TPCH data set, but just to give you an idea of tables and joins and so on. So what does that leave you with? Well, extreme performance. That was the key element, the key goal that we set ourselves when we started out. But we actually set ourselves a constitution, if you like, 4 goals that we wanted to achieve with Brytlyt. The first was real-time performance, and we get that from the GPUs. The second was to be able to easily integrate what we've got with existing investments in technology and infrastructure, be easy to use, and also be easy to extend. And now those last 3 all come from the fact that we've actually integrated with Postgres. So we've taken our technology and rewritten large parts of the Postgres source code, the Postgres database engine. So from a user perspective, what you're looking and working with is Postgres, and all the tools and connectors and stuff that you get from Postgres you'll get out the box with Brytlyt. But the back end, the engine actually runs on GPU, so significantly faster. If you drill down into what the user is actually going to be dealing with, in the orange block you've got the Brytlyt software running on GPUs. And that software then exposes SQL-type operations via an API. We've tightly integrated that with Postgres, so the first tool that users will use to interact with the system is Postgres, and all the standard Postgres tools, pgadmin, and all the visualization tools, PSQL, the command line, if you like. On the on the right-hand side, you've got Tableau, Power BI, MicroStrategy. They all have Postgres connectors, so they will work out the box with Brytlyt. We've also, however, developed our own visualization tool called Spotlight, and this has a geospatial element in it. I'll get onto the demo at the end of this presentation and show you what I mean. But when it comes to geospatial data, it's really useful to be able to visualize it on a map. There's often millions, if not billions, of data points in the data set that you want to visualize, and visualization tools today just aren't able to deal with that kind of a volume of data, because those 3 all render the images locally on the client. And that means that if you want to render 1 billion data points, they need to come across the network and end up on the client. What we've done is built a rendering engine on the database side on the GPUs. So the GPUs are not only used for aggregating and running SQL workloads, they're actually also used for generating the images that you would then overlay on a map. And then finally, there's Torch and Jupyter. So this is really interesting because when we are looking at our memory management module for Brytlyt, we realized that Torch has got a very sophisticated memory management capability. So we Torch, the memory management module there, extended it, enhanced it, and used it as our own. But what's really cool there is that from the computer perspective, whether you're looking at a column in a database, in a table, or a tensor that is going to be consumed by a machine learning or AI workflow, it looks exactly the same. So you can use SQL to work with your data, create the data, load the columns in a table, and with zero copy, then that data can be consumed by a Torch workload. And we've also integrated Jupyter. So what you then have is a web-based front end, a workbench, that you can run your visualizations, you can run your SQL, and you can run your Torch workloads as well. At the bottom, you've got all the mechanisms that you can use to get data into the platform. It's all based on Postgres. Postgres natively has a thing called a foreign data wrapper. And basically what that means is you can connect to virtually any data source that you like. It's open source, so I think there's about 60 data connectors, foreign data wrappers, Postgres data wrappers at the moment available in the community. You can connect to flat files, you can connect to Microsoft SQL, Excel, CSV, MySQL, Hortonworks, Oracle, whatever it is, very easily just by a single line of code, suck data into the platform. We are partnering with IBM, and what that is doing is bringing best-in-breed IBM Power hardware with the next generation of GPU accelerated databases and analytics. We're very excited about that partnership. You've probably heard a lot of talk about NVLink. One of the key issues when using GPUs to accelerate data is the bottleneck in getting data on and off the GPUs. And NVLink has a very neat solution for that, 4 to 5 times faster than comparable x86 type architectures, which rely on the PCIe bus. So just to go through that a bit more, if you look at Power 8 architecture, that is the NVLink that connects the GPUs to the Power 8 CPU and gives you 80 gig bidirectional data uplink speeds. That is half of a typical Minsky server. You actually have 4 GPUs in a server, 2 sockets, and there's a bridge between the 2 sockets. So let's just talk a little bit about Postgres. If you look at straightforward vanilla Postgres, this is what you'll get. It's got a user client like pgadmin or PSQL, a parser that then takes the user query planner, hands it over to the DB engine, and there's a bit of disk storage in there. I mentioned a little bit about the foreign data wrappers. That allows you to connect to third-party data sources. And if Brytlyt was just an extension, then basically we would be using the foreign data wrapper as a third-party data source, right? But what we've actually done is integrated tightly with the database engine. So Brytlyt is actually a fork of Postgres. We made very big changes, rewritten large parts of the database engine to run on GPU, and therefore the data is uploaded onto GPU and stays there, and then you can run all your SQL workloads off that data once it's already on GPU. We also have integrated with MariaDB. Last month we announced at the M18 conference, MariaDB's annual event, that we will be partnering with MariaDB. Very interesting partnership there. It gives us the ability to get our technology into hands of millions and millions of users who can then really take advantage of it. And if you look at MariaDB, it's one of the, or if not the fastest growing databases on the market today. So this is a graphic from DB Engines, and the bottom in yellow you can see the accelerated adoption of MariaDB. It does mean that an element of our code is going to be open sourced and packaged up within the MariaDB environment. I mentioned to you about the Torch integration and how we are using the Torch memory management module, and that means that we have a product called BrightMind, which brings SQL and AI together with GPUs with zero copy, and that is really, really useful for analysts and data scientists. because it means that they can use the SQL to prepare the data, which takes up most of their time, and immediately begin running machine learning and AI type workloads on that data that they've prepared, all happening on GPU. So there's a little bit more going into a bit more depth of what that means. You've got your GPU RAM. If you create an array in that piece of memory, you can access that array directly via SQL, do your data definition language, data manipulation, all via Postgres. And then you can hand that over directly to Torch and run your AI and ML operations via Torch. Zero copy, very efficient use of GPU hardware, but also really efficient for data scientists in their workflow and the time that they are spending. So Spotlight is the front end, the workbench that brings SQL and AI together and allows you to run interactive analytics on billions of rows of data. So I'm going to jump onto the demo now. So this is the Spotlight front end, the workbench, browser-based. The data set is telco data, basically user experience data, so it contains signal strength, upload speed, download speed, a couple of latency, a couple of other metrics, as well as date and time, and then also location. That's 160 million points that you can see on the screen there. And if I wanted to navigate in there and have a look at the data, sorry, let me just refresh this. Oh, looks like we've got a Wi-Fi issue here. Let me just take this out. Well then, back up and running. Okay, so, right, let me just shift some data around here and get this out of the graphics a lot more neatly put together. Pop that over there. Right then, sorry about that. Mobile user experience data. This is 160 million data points, and I can dive in there. You can see the tiles being generated on the server in real time, and you can also see the GPUs updating these graphics in real time. This point map, geolocation point map, is showing the rendering engine running on GPU and generating the tiles for this visualization. I can also pop in a sub-selection within that map. And drag that selection over, and everything will update in real time. A bit more data. There you go. Cool. So the workbench is a range of visualizations that we can look at. So there's a line chart. I can choose my table and columns and so on. Be quite specific on what I want to be looking at. I've got a number of charts that I can pick from: table, bar charts, histograms, point maps, pivot table. This pivot table is quite interesting because I can actually drag and drop columns around here. Put that back. So a very powerful visualization tool with a geospatial capability. I can also jump in here and run SQL queries. And then what's also pretty cool is I can directly connect to Jupyter from within the front end. I'm going to give you a little demo of Brytlyt. So what we have here is time series data from Quandl, financial ticker data. Load some, this is all Lua. Load the modules I need, get the data, split into a training set and a validation set, 80-20. I'm going to be creating a window, a moving window of 20 days. There's one data point per day. Train the data set, train the neural network, create the neural network. It's three-layer network. Train it, and then use that trained network to make predictions on the 20% validation set. Now, we didn't spend a lot of time creating a really accurate model. This is really just to showcase the capabilities and how everything integrates together, and also showcase the workbench. But even so, you can see that the model that we have created is pretty accurate. So in blue, you have the real data, the 20% validation data set. And if we give the neural network 20 windows of data, the neural network will then make a prediction on what the next day's data is going to be. Yes, sir?
Are you using that notebook to fetch raw data from, or like Brytlyt engine, Brytlyt, sorry?
So,
or are you actually executing something against the engine when the notebook model runs? It looks like you're just fetching the data much like you're calling Postgres.
so that particular demo, ultimately, we are running the notebook directly on data on the GPUs already. This,
So there's a bit of a...
there's a PG connect there, that's right. So this is a slight,
To fetch the data, there's a PG connect.
that's right. So this is a,
When you're running the model.
so this is an old demo, and what we have now is that would not be there. You would basically be running directly on the data that's on the GPUs that's in the database. So you're absolutely right. This model shows us creating a database and then fetching the data out of it. But
I guess what I'm saying is there are things inside Jupyter that allow me to do machine learning and such.
sure.
If it's not available through the SQL of PG Connect, then there's no interaction here, is there?
Correct.
Okay. So you're not doing general purpose things on the GPU, it's only against the data that's exposed through a SQL.
No. So what we've done is,
Okay, I looked at your diagram, it's about Torch. I think I missed something.
yeah, it's about Torch. So specifically for Torch, if you're using Torch to do your machine learning and
There's something in that notebook that called Torch to do the...
correct. So I think there's probably a Torch module up here somewhere. There you go.
Okay.
Okay.
Missed that when you scrolled through.
Sorry, yeah. So specifically for Torch, you use SQL to prepare tables and columns, and that column
And
is,
in the GPU, Torch just accesses what you prepared.
exactly, got it? And that's pretty much the presentation. Any other questions? Yes, sir?
It's not clear to me
So the IP is specifically around being able to do joins in parallel efficiently. So joins can be done in all sorts of different ways. You've got hash join, merge join, nested for loop, index nested for loop. Hash join is very fast, but the predicate needs to be in equality, and you need to create a hash table for one of the tables, right? It's also parallelizable. Nested for loop is parallelizable, but grows exponentially with the size of the data set, and quite often a lot of that work is unnecessary. So you can do things like on GPU nested for loop joins, but you get the data workload becomes so big when you start looking at billions and billions of rows of data that it can take years literally to process the join. So what the IP specifically targets is being able to run joins in parallel efficiently, far more efficiently than nested for loop, even more efficiently than hash join. So our IP allows us to run joins, process them more quickly than hash join, and also gives us the scope to run on GPUs very effectively. Any other questions? Okay. Thanks very much for your time.